Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on December 27, 2025, about 5 days ago. This paper introduces Bayesian wind tunnels, and it shows that small transformers can match analytic Bayesian posteriors with 10 to the minus 3 to 10 to the minus 4 bit accuracy, while capacity-matched multi-layer perceptrons fail by orders of magnitude. The paper is titled, The Bayesian Geometry of Transformer Attention. Okay, and as we'll see later, the geometric story of how attention enables that Bayesian-like behavior is the really striking part. Alright, the previous discussion set up the bijection wind tunnel, and Figure 1 shows the core behavioral result. The left panel plots predictive entropy versus position in the sequence, and the transformer curve sits almost exactly on the analytic baseline, while the capacity-matched multi-layer perceptron stays high and barely shrinks uncertainty. The right panel makes the gap stark, because transformer calibration error stays near 0, while the multi-layer perceptron error climbs past 3 bits. Okay, while the previous figure showed perfect average calibration, Figure 2 checks whether that fit holds per sequence. Figure 2 shows 8 panels, labeled Path 1 through Path 8, and each panel overlays the transformer's solid entropy curve on the dashed analytic Bayes curve. The key pattern is the staircase or sawtooth shape, because entropy drops in discrete jumps when new pairs eliminate hypotheses, and it collapses near 0 when an input repeats. Well, after the bijection task nailed per sequence behavior, Figure 5 shifts to the hidden Markov model wind tunnel and asks whether the transformer stays calibrated as sequences get longer. Figure 5 shows 3 panels for length k equals 20, 30, and 50, and the solid transformer entropy almost perfectly overlaps the dashed Bayes optimal curve. The red dashed line marks the training boundary at position 20, and the lack of a visible kink supports a position-independent recursive update. So, Figure 5 showed that the transformer stays well calibrated, even past the training horizon in the hidden Markov model wind tunnel. Table 1 summarizes that story numerically by reporting mean absolute entropy error, which measures how far the model uncertainty is from the analytic Bayes uncertainty. The transformer stays near 0 at length 20, and only rises to about 0.013 at length 30, and about 0.029 at length 50. The capacity-matched multi-layer perceptron sits around 0.40 bits at every length, so it never learns the recursive belief update. Alright, Table 1 quantified the tiny entropy errors, and Figure 8 stress tests whether the model is truly doing Bayesian filtering rather than memorizing state identities. Figure 8 shows a scatterplot of mean absolute error before versus after permuting the hidden Markov model hidden state labels with the dashed diagonal marking perfect invariance. Most points sit close to that diagonal, which means the calibration barely changes under relabeling. That invariance supports the idea that state indices are treated as pure symbols. Okay, Figure 13 adds a mechanistic check on where the Bayesian update actually happens. Figure 13 shows 2 line plots of probe delta mean squared error across layers, with attention on top and feed-forward networks on the bottom. The attention curve spikes early and then flattens near 0, which suggests attention changes what information is routed, but does not steadily improve the numeric belief readout. The feed-forward network curve stays negative across many layers, so the feed-forward networks drive most of the entropy prediction improvement. Alright, Figure 13 argued that feed-forward networks do most of the numeric belief updating, while attention mostly routes information. Figure 18 pulls the full mechanism together in 3 stages, so the story stays consistent across both wind tunnels. Layer 0 creates a key value hypothesis frame, which acts like a coordinate system for which hypotheses are still alive. The mid-layers then do sequential elimination in the residual stream, and the late layers refine precision by organizing values onto a low-dimensional posterior manifold. So 2 takeaways stand out. The first takeaway is that Bayesian wind tunnels let you verify, in closed form, that a small transformer really matches Bayes' optimal uncertainty, while a capacity-matched multi-layer perceptron collapses. The second takeaway is the mechanism, where residual streams hold beliefs, feed-forward networks do the numeric update, and attention routes the right pieces. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.